Good to see you all again. We are back today with Sanghyun, who will present us another technical talk this Tuesday. But before we start, let me make two short announcements. Registrations are open to our upcoming trainings in Germany. We plan to run them physically, but if the government regulations do not allow us to do so, we will move them online and conduct them via Zoom and Discord. We will announce the exact location in the middle of March, and if anyone is interested, please check out the trainings on our website, and if you have any questions, just drop an email to our email address info@hardwear.io.com. Another announcement is that if anyone from the audience has an industry-related job opening, let us know, and we'll be happy to announce it on our jobs Discord channel. Just send us the job description and we'll do the rest for you. Today we have Sanghyun with us, who is a PhD candidate at the University of Maryland College Park. He will present today his research in which he will address some practical hardware attacks on deep learning. As usually, today's webinar will consist of a 30-minute technical talk followed by a 10-minute Q&A. If you have any questions, please drop them in the Zoom chat box and we will answer them after the webinar is complete. Please don't forget to share your feedback with us at the end of the webinar and give a shout out on social media to our speaker today. Without further delay, I would like to invite you to start your presentation.
Okay. So can you see my screen?
Yes, everything's good.
All right. So hello, everyone. Great pleasure to be here. So my name is Sanghyun, and I'm a PhD candidate at the University of Maryland College Park. Today, I'm here to talk about how an adversary can exploit hardware-based attack vectors to jeopardize deep learning systems. So in particular, I want to show that in this talk, the deep learning models have computational properties that traditional software do not have, which makes them particularly vulnerable to hardware attacks. So let's start. So before we start, let's think about our future with deep learning. So your model will write the firewall rules. This example from the OpenAI shows that a large-scale language models trained on an enormous corpus of text data sets can generate the firewall rules from your human language. Once we type, for example, firewall all incoming connections to port 22, then the model returns the corresponding IP table rule. And your model will also drive your car. This example shows that how deep learning models in Tesla's autopilot system recognizes your driving environment. And based on this visual recognition, the model makes decisions how to accelerate, slow down, or stop your car. And a model will assist your surgery. Recent work uses deep learning models to interpret the surgeon's hand movement precisely in complex surgeries or to reduce the variations in the surgical procedures. And moreover, a model will even be used for surveillance systems. And this example used the deep learning models to monitor and identify potential suspicious people from the security cameras. So now we've seen that deep learning models will be deployed in the various computing platforms that we face everyday lives. And this means that the security of those deep learning models is becoming more and more important. And this makes many researchers and the practitioners think about what are the potential attack surfaces to the deep learning systems and how we can make them secure and reliable. So let's see how this goes. So to answer these questions, research in the field of adversarial machine learning studies the attack surfaces. For example, first the models. An adversary can manipulate the model's behavior by feeding malicious samples during its training. So once attacked, for example, the model becomes like this Microsoft chatbot tape that turned into a racist after 24 hours of its release by learning bad tweets. And another threat is the adversarial examples that aims to manipulate the model's prediction by adding imperceptible perturbations to the input when the model is trained up and running. And you can see the most famous panda in the world that turned into given when we see a small amount of noise crafted for this misprediction is added on the panda. So by studying those attack surfaces, researchers came up with certified defenses which provide a mathematically provable guarantees, such as robust statistics that provide the resilience to some malicious samples or adversarial training against the maliciously perturbed inputs. So now the question is, can we say that our models are secure and reliable? So can you put those certified models in self-driving cars or surgery robots? So you might think it may not. Something is missing. So I'm going to show what is missing actually. So prior work mostly studied the security of the deep learning models, considering them as a standalone or mathematical concept. And in consequence, we study the model's robustness against attack in an isolated manner. And more importantly, this perspective often overlooks the impact of the hardware or the system level vulnerabilities. So let's think about this. So once we train the deep learning models, mostly deep neural networks, and when we want to deploy them to the real world systems, such as self-driving cars, IoT devices, or the cloud infrastructure, we require hardware and supporting infrastructure, or deep learning frameworks such as PyTorch, TensorFlow, or Objects, and even databases and many other software components such as Cassandra or the Elasticsearch. And the problem here is that each of those components can be subject to adversarial pressure, which means that we need to consider those new attack surfaces and examine how deep learning models can become vulnerable by attacking them. So for that, I propose a new perspective. So I propose to look at deep learning models as another computational tool or software running on the hardware and supporting frameworks. So from this unique perspective, we can easily imagine that deep learning models may become vulnerable to existing hardware or system level vulnerabilities. And more importantly, those models have computational properties that the traditional tools do not have, as I said before, which makes them particularly more vulnerable to hardware or system level threats. So in this talk, we limit our scope to the hardware vulnerabilities. So let's think about why we focused on hardware attacks. Well, hardware attacks are known to be very powerful because those attacks can break mathematically proven security guarantees. So in fact, prior work shows that exploitation of hardware attacks against the cryptography, for example, such as fault injection or side channel attacks on encryption algorithms. And I want to say that this is important to know. This is not because cryptographic algorithms are weak. It's because hardware attacks were outside of their mathematical models. So, but wait a minute. So isn't it difficult to perform hardware attacks on local machines? Yes, because you need to break network defenses to let the victim download and run your malicious software, and even make the victim run it when you're doing an actual exploitation. Then this is difficult, but there's an environment where the exploitation of hardware attacks has been shown practical: the cloud. So recent work showed many exploitation of hardware attacks in there. So there are clear benefits that the attacker can have in the cloud. First, the co-location. So in the cloud, there is a chance that an attacker and the victim's virtual machines share the same hardware, such as CPU or DRAM, which is memory. And second, once the co-location has been made by an adversary, the attacker can remotely exploit hardware attacks without accessing to their virtual machines. So however, in the meantime, also cloud providers try to make their services secure, right, against those hardware threats. So the strong attacks who can make the fine-grained control over their behaviors becomes more and more infeasible. For instance, it would be challenging for Rowhammer attacker to flip a specific bit in the memory of the victim's virtual machines because of the defenses such as address space layout randomizations, which is known to be ASLR. So weak hardware attacks but still exploitable. For example, a blind Rowhammer attacker who can flip bits in the memory randomly. But however, those attacks are usually considered in the literature useless in inflicting severe damage to a system, right? So in the rest of my talk, I'll focus on showing that this is not the case, especially for these deep learning systems. So our research started by asking this simple question: how vulnerable are deep neural network, which is the heart of the deep learning system, to weak hardware attacks, right? And we found that weak hardware attacks can inflict the severe consequences on deep learning systems. So today, I'll review the impact of the two well-known, well-studied hardware attacks on deep learning systems. First, fault injection attack, which is Rowhammer, and second, a cache side channel attack, which is flush rewrote. And specifically, I will expose the computational properties of deep neural networks, which can turn these weak hardware attacks into a significant threat. So let's first talk about our research that concerns Rowhammer, a well-studied fault injection attack. And in this work published in Usenix 2019, we exposed the graceless degradation property of deep neural networks, showing that the network performance can drop significantly by flipping a single bit in the memory representation. So let's start from this. So in 1990, a computer scientist, Dr. Jan LeCun, published a seminal paper titled Optimal Brain Damage. And this is the seminal work, which is the first that reported the graceful degradation property by showing that you can remove 60% of your model parameters without the accuracy drop. And suddenly researchers came up with a bunch of techniques based on this intuition. For example, they do pruning to reduce the computational cost of inferences, or they do quantization to reduce the network sizes, and even they blending noises to the parameter spaces to provide some resilience against the adversary examples. And all these techniques achieve this benefit with the negligible accuracy drop, which is within 1%. And the prior work in security also showed that even if you try to degrade the accuracy, it's difficult. First, they blend a lot of poisoning samples, which is the malicious training data, to try to degrade the accuracy, and they cause a lot of random bit errors, or they cause hardware fault randomly. But the maximum accuracy drop they could observe was 11%. But the problem here is that all these practices gives us false sense of security about the neural network resilience against the parameter perturbations, because they focused on the best case or the average case perturbation scenarios, not the worst case ones that an adversary can cause. So let's look at what's happening in detail a little bit. So here we display the 4-layer convolutional neural network that has 2 convolutional layers and 2 fully connected layers, and trained on NList. So the network has model parameters described as blue boxes, optimized in training, and are used in inferences to classify images of the digit correctly. Of course, it has the accuracy of 99%, which is pretty high. And let's see, once the model is loaded, this is how the parameters are located into memory while the network is in use. So you can see each of the weight and biases takes up the continuous address space, and the size of those parameters in memory is larger than that of the code running in the model. So this is the picture how the memory representation of your deep learning process will be. And here I illustrated an example of the prior work's perspective on a model's resilience against the parameter perturbation. Suppose that you manipulated 5 parameters in the last layer. And from the conventional perspective, the error is a small change in the numerical representation of a value from 0.3 to 0.02, which has a negligible impact on the model's accuracy. But what would be the worst case parameter perturbation? So for the same parameter, an adversary can flip the most significant bit in the exponent from 0 to 1. And then the value changes exponentially, and the accuracy of the model dropped significantly from 99% to 57% with that small change. And this illustration exactly shows the worst case scenarios where a single bit flip leads to a significant amount of damage to a deep neural network model. So now we see that the graceless degradation of a neural network, that a small perturbation, a single bit flip lead to a significant accuracy drop. Then our next step would be to quantify this vulnerability by asking that what would be the maximum accuracy drop of deep neural network caused by a single bit flip? And in many deep neural network models, how many model parameters are subject to a significant accuracy drop by flipping such a bit? So to quantify this vulnerability, we decided to flip all the bits in the deep neural network model one by one. So here's what we did. So we first take the model and flip each bit in all parameters into two directions, 0 to 1 and 1 to 0, and measure the accuracy drop over the entire test data set. So we also defined the term an Achilles bit for referring to a bit whose flipping can cause the accuracy drop over 10%, because the 10% is the upper bound empirically found by the previous studies. So then we look at two things in each model. One, we look at the maximum accuracy drop can be caused by a bit flip. Two, we measure how many parameters are become vulnerable in a model. So here we say a parameter is vulnerable when it contains at least one Achilles bit whose flipping can lead to an accuracy drop over 10%. So we first examine 8 convolutional neural network models trained on NMIST. They have different architecture configurations, and we flip each of the 32 bits in thousands of parameters in a model. What we found here is that in each of the all eight models, there is at least one Achilles bit that causes an accuracy drop of more than 98% once the bit is flipped, which is quite surprising because if the model is completely random, the accuracy would be 10%, but actually the flipping that specific bit leads to the accuracy drop that makes the model more horrible than random. And we also found that almost half of the parameters contain at least one bit that can cause an accuracy drop more than the empirical upper bound to 10%. So in addition to that, we observed that dropout and batch normalization cannot reduce this vulnerability. So in this table, B dropout models, we add the dropout layer to the base model. And in B-DP-norm, we add the batch normalization layer to the B dropout network. And why this result is interesting? Because this result implies that even if dropout and batch normalizations are the training techniques used to remove the dependency of a model's prediction on a set of specific parameters, but they do not helpful in mitigating this vulnerability. So we just expand our perspective. We also look at 11 larger models with different architectures, and the analysis outcome was consistent. Here we examine the exponent bits in each larger model, as they mostly cause the accuracy drop more than 10%. In all the architectures and the parameters that we examined, each model has at least one bit whose flipping can inflict an accuracy drop up to 100%. And also almost half of the parameters that we examined are vulnerable. So this research implies that this vulnerability is not specific to a model. It's not just a single worst case, but it's a general vulnerability that exists across many data sets, architecture configurations. So now the question becomes, can a weak attacker really exploit this general vulnerability? Let's think about this together. Let's start from a single bit adversary. Here I show the two axes based on the adversary's capability and the knowledge. So first in the vertical axis, the attacker becomes a surgical when she can flip a bit in an intended location in memory, whereas the attacker with no control over the bit flip location cannot. And in the horizontal axis, the white box attacker knows the victim model's internals, knowing which parameters are vulnerable, whereas the black box or blind attacker is not. So what would be the consequence? The strong attacker is in the upper right quadrant, which knows who knows which bit to flip in a model and can flip that bit. So this attacker can easily control the performance degradation of a victim model from 0 to 0 and up to 100%. But on the opposite side, there's the weakest attacker who doesn't know which bit to flip and cannot even control the bit flip location. And in this case, the probability of hitting an Achilles bit would be much, much lower, and it has a negligible impact on the accuracy drop. But is it the case? Suppose that the weakest attacker flips multiple bits randomly in the same model. Then the probability of hitting an Achilles bit increases because half of the model parameters contains at least one Achilles bit. And in consequence, a weak attacker can quickly turn into a stronger attacker. So, we got this. So we evaluated this weakest attacker armed with multiple bit flip capability. So we consider the typical deep learning deployment scenarios in our evaluation, which is deploying model to the cloud, where a dedicated virtual machine is used for deploying the deep neural network and running under the Rowhammer pressure. And we run our Rowhammer attack with this setup. Here I will not go deeper into the configuration details. You can check them in our paper. But in summary, we consider the Rowhammer attack that randomly flips bits in the process memory. And we run this attack on multiple DRAM chips. And also we run sufficiently many bit flip attempts so that we can generalize the impact of this weak hardware attack instead of just showing that one case of exploitation. So our expected consequences are A, you can expect a process crash. B, you can expect our attack hit any bit that doesn't lead to the serious accuracy drop. Or you can expect that our attack can cause the accuracy drop over 10% by hitting an Achilles bit. So here is the summary of our result. In 62% of our attacks, the attacker can cause an accuracy drop over 10%. And also the time it takes to cause that damage is almost within a few minutes. And further, our attacker can remain inconspicuous because we observe only 6 program crashes over the entire 7.5 K bit flip attempts. So what it means, then our research shows that a weak version of the Rowhammer attacker can easily degrade the performance of deep neural network models running in the cloud over 10% within a minute. So in the next part of my talk, I'll move our focus to the side channel attacks. Okay, so let's talk about how an adversary can exploit side channel attacks. So in this research, we start from this question: can a side channel attacker steal deep neural network architecture by exploiting a small amount of information leakage from side channel? This is practical threat as many side channel attacks have been exploited in the cloud to extract secrets. So some may argue that we already know many deep neural network, which is ResNet or VGG or whatever, but we do not steal such generic architecture that everybody knows. We steal unique neural network architecture shown here, which is far from being generic. And in reality, those architectures carry a lot of incentives to steal. First, unique architectures outperform the off-the-shelf architectures. For instance, EfficientNet is the currently state-of-the-art on ImageNet. Transformers are known to be the state-of-the-art on language models, and so on. So stealing is good. In addition, constructing unique architectures takes a lot of time and effort. Running the architecture search algorithms like neural architecture search takes thousands of GPU hours, and even handcrafting unique architectures demand 5 to 10 machine learning experts. And in consequence, once the unique architecture is found, they become intellectual property or trade secret. And by stealing those unique architectures, the attacker can train a functional model with the same accuracy as the victim and achieve high performance on even different data sets. And even they can do further attacks that exploit the architecture information, which is stolen by our attack. So now the remaining question is, how can an attacker reconstruct unique neural network architectures by leveraging a small amount of information leakage from side channel attacks? So here our work introduces an algorithm that reconstructs the unique architectures only by leveraging cache side channel information observed while a model is processing a single input. Specifically, we will show that here there are regularities in deep neural network computations, which makes the reconstruction particularly easy for the attacker. So to illustrate how our reconstruction attack works, I prepare a simple neural network on the left side, which is a residual block. And our attacker uses flush reward, a remote cache side channel attack, exploitable in the cloud remotely. So when the network processes a single input, the attacker runs flush reward, and the computational trace that the attacker observed is shown on the right side. So it's a little bit noisy. And then with this trace, what the attacker needs to do is to reconstruct the victim's architecture and configurations from this trace. And for that, our attacker needs to identify A, the computational graph, how the connections between layers will be, and B, layer configurations such as kernel sizes, trie channels, or input and output dimensions. And it is not an easy task as the search space is almost infinite. Thus, previous studies make an unrealistic assumptions that the attacker knows the architecture family that a victim uses, such as they know that the victim uses ResNet family, but they try to figure out which ResNet they're actually using. However, in our work, which is different, we figure out that if you look at how we perform deep learning computations, there exists some computational regularities that an adversary can exploit. First, we compute the layer in a neural network sequentially. So we can find this regularity in the flush reward trace. We can see there is a convolutional 2D first, and there are some computation traces, and you can see the batch num and ReLU and so on. And you can using this trace to reconstruct the layer sequences, but the real challenge happens when we have multiple connections. Here, the add, a binary operation, can be connected to any preceding layers, which result in multiple architectures from the observed trace, like this. So how you're gonna solve this problem? Well, we take the very simple solution. We just populate all the possible candidate architectures and try to prune incompatible candidates later on. So for pruning, we reconstruct the two types of information. First, the layer configurations such as kernel sizes, and B, the input and output dimensions of each layer. And we do this reconstruction for each of the candidate architectures and try to prune them. So here we exploit the second computational regularity. The time it takes to process each layer depends on the layer configurations. In detail, deep neural network computations are mostly matrix multiplications. Therefore, we can estimate the size of the matrices considered in each layer's computation. For those matrix size estimations, we combine additional information such as GMM calls that indicate the number of for loop iterations in matrix multiplications. So by just counting how many times this function call happens, you can count the number of nested for loop iterations. And then using this information, you can reconstruct the matrix sizes. So combining all those information, the attacker now has the computational graph and the layer configurations, as you can see on the right side. And I'm not gonna also go into too much details. You can find these details about how it did in our paper. But using this information, we can finally eliminate incompatible candidates. So we evaluate our reconstruction attack on two unique deep neural network architectures, Malcolm and Proxylist-NAS CPU. And we attack them while they're running in the virtual machine in the cloud. And here is the summary of our evaluation. We first figure out that we can reconstruct both the unique architecture with zero error. And we also figure out the time it takes to reconstruct is much less than the time to construct those architectures. For example, when you try to steal the Proxylist-NAS CPU architecture, it just takes 12 CPU hours. But if you try to create these architectures by using neural architecture search algorithms, it will take 40K GPU hours on a machine, which is pretty higher than like the time it takes to reconstruct a model. So this work shows that by using this noisy information, which is kind of regarded useless, extracted from the cache side channel attack, an adversary actually can reconstruct unique architectures with zero error. So now the conclusion and implication part. So far, we propose to view neural networks as one of the components that consist the computer systems, not a standalone concept. And from this perspective, we need to re-examine the interplay between the models and other system components with the security mindset. And second, with this security mindset, we need to think about the vulnerability of deep neural networks. We think that this vulnerability of neural networks to microarchitecture attacks is under studies. And to study such vulnerability, we need to understand the worst case behaviors when we design deep neural network systems. And specifically, this worst case could be different from what we have known so far. So we need to examine whether the computational properties that deep neural network will have can make it feasible for a weak hardware adversary can inflict the worst case. And lastly, against the deep learning systems, system-level defenses may not provide a complete view of security, as weak hardware attacks can lead to a significant damage to a model. So therefore, we need to consider a hardware-software co-design approach for closing hardware attack surfaces against the deep learning systems. So this is the end of my talk. And we also have a nice write-up about our research on this website, hardwearfail.ml. And please check that out. And from now on, I'll be happy to answer any questions from the audience. Thank you.
Thank you very much for your presentation. Let's see. Are there any questions? Would anyone like to ask something from Sanghyun? Yes, I think it was quite a technical webinar, but oh, we got one now. I got a question. I study ML application on space systems. We may have attacks due to natural environments, such as high energetic particles. Are there studies on the vulnerability of system due to single event upset?
I couldn't find such previous studies, but I remember I found some papers that actually study the vulnerability against the solar energy particles on the hardware that actually running deep learning systems. But this study also had some problems because they just measure the impact by averaging the impact of the multiple particles. So it's the pretty much like average case scenarios. But in order to look at what the consequences really be, we need to think about like how each particle actually, how much impact of each particle on these deep learning models running on hardware. So I propose maybe like not using those previous studies, but try to look at the worst case scenarios and try to find the worst case scenarios of your deep learning models will be kept on the space systems. So which will be right way to come up with some security specifications for that system.
All right, thank you for answering the question. Are there any more questions? You can send it also directly to me or in the Zoom chat. Yes, I think this was all. We don't have any more questions. Thank you very much once again for delivering this webinar. Guys, next Tuesday we'll have another webinar titled Stealing Secrets from Intel Vaults with side channels and voltage faults. You can find more information about this on our website. Please don't forget to fill in the feedback form, which is in the chat box and which will also pop up for you after the webinar is over. And thank you once again for the webinar. See you next week and have a great week ahead.
Thank you very much, Andrea, and thank you for listening my talk.
Thank you very much, Sanghyun.